So let's do some example problems, all right? First problem says, a pool ball leaves a 0.6 meter high table with an initial horizontal velocity of 2.4 meters per second. Predict the time required for a pool ball to fall to the ground and the horizontal distance between the table's edge and the ball's landing location. Okay, let me just change pen colors here to something nice. Let's do yellow. So I'm just going to draw a picture of the problem real quickly. Here's a table, okay, and there's a ball on it, and it's going to be launched over this table with a initial velocity in the x direction, and because it says horizontal, initial velocity in the x direction of positive 2.4 meters per second. Okay, so that's like my little picture I'm going to draw here, okay? The next thing I'm going to think about is I'm going to use to the right as positive and up as positive. Those are my axes, okay? So if anything's down, it's negative, and anything to the left is negative also, okay? Now, with this guy, oh, one other thing that they tell me too, sorry, I should have put this in the picture, is that it leaves the table that's 0.6 meters high. So this distance from here to there is 0.6, and it's actually negative. Sorry, I should have put that a little bit further. Negative 0.6 meters. Why? Because it's down, right? It's starting here and it's going down. So it's 0.6 meters, negative 0.6 meters down. Okay. The next thing I'm going to do is I'm going to create a table, okay, to list all my kinematic variables. And I'm going to put the x ones here and the y ones here. Okay, so what are the 5 kinematic variables? Well, you have v sub I, v sub x, a in the x. I'm going to call it d in the x, and I'm going to call t time. Okay, so I just listed all those. Now, let's do it for the y. V sub I, y. Oh, sorry, I should have called v final. Sorry about that. V final y, a y, dy, and t. And I'll be honest with you, if you want to, not put the little y after it because you kind of made this chart, that might be a little easier. But it's up to you. You have to figure out what works for you. Now, what do I know that is the initial velocity in the x direction? Well, it's positive 2.4 meters per second. And I'm going to leave the units off right now just to kind of make it a little bit clearer. Now, what will the final velocity be in the x direction? Well, remember, this is a projectile motion problem, and so the initial velocity in the x direction is actually equal to the final velocity in the x direction. Even though the problem doesn't say it, it is plus 2.4 meters per second. And the reason why is because we basically ignore air resistance, and it's just, there is no force. No horizontal force means no change in velocity, okay? Now, is there an acceleration in the x direction? The answer is no. Right? There's nothing that's causing this ball to accelerate in the x direction at this point anymore. Okay? I mean, clearly someone must have pushed this ball to make it roll across the table, but after the push, there's no acceleration. Right? The distance in the x direction, well, that's what we're trying to figure out, right? We're trying to figure out the horizontal distance. So I'm going to mark that with a big old question mark. What is the horizontal distance? Okay? Predict the time required for the pool ball to fall to the table. The time required. So that's a question 2. Okay, so now I just did all my x stuff. What about y? The initial y. This is a thinker kind of thing. Do I know the initial velocity in the y direction? And you may be saying no, they don't tell us that, but actually we do know it, right? Is there an initial velocity in the y direction? Is anything causing this ball to fall down as soon as it leaves the table? I mean, to move downwards. And the answer is yes, there is gravity, but initially it starts at 0 meters per second. And this is one of those things where in these types of problems, you have to not be afraid to say, this is 0. Okay, 0 is okay. You certainly can use that number. Okay, so don't be afraid to use it. The v final in the y direction, we don't know, okay, but I don't think the question's asking for what is the final velocity of it as the ball hits the ground. So I'm just going to leave that with nothing for right now. What about the acceleration in the y direction? Well, what's causing this ball to go down in the first place? Well, it's gravity. What does the acceleration do to gravity on Earth? Well, it's negative 9.8 meters per second squared. Okay. Now, what distance in the y direction does the ball fall? Well, it tells us that it falls 0.6 meters, right? Because the table is 0.6 meters high. So I'm going to write negative, I'm sorry, I almost forgot it again, negative 0.6 meters. And the time, well, I don't know. So you can see why time is the important one to figure out, because the time in the x and the time in the y is going to be the same. Once we find out time, we know the answer for both of those because it's the same. So what equation should I start with? Well, I want to figure out time, and I'm thinking I want to work with some of the y variables. So I'm going to actually use this equation where it says d equals v sub I y times t plus 1/2 at squared. So this is one of the 5 kinematic variables that I gave you guys on the on one of the previous slides. You'll notice I labeled this as vi sub y. And why did I do that? Well, it's because I'm talking about the initial velocity in the y direction, okay? Not the x direction, in the y direction, all right? And the reason why I'm picking this one is because I know all these variables except t, okay? And t is something I want to figure out. Okay, so let's plug in some numbers. And I'm going to change pen colors here so it's not so monotonous. D is negative 0.6 meters. V sub I, y, is 0. So that's really cool. This whole thing cancels out here. So I have 0 plus 1/2. And then what is my acceleration in the y direction? Negative 9.8 times t squared. Okay, and basically, if you do this algebra, okay, which does involve a little bit of square rooting and that type of stuff, you should get a time of about 0.35 seconds. Okay, so it takes about 0.35 seconds for this marble to fall to the ground, and that is my time for actually both of these variables. Right. Now, the next thing I want to figure out is the distance in the x direction. Well, if you remember, if there is no acceleration, or I'm sorry, if the acceleration is 0, we can use this equation, d equals vt, okay? And you may say, well, why don't we just use that equation first? Well, we didn't know t, right? And we didn't know d, so if you have 2 unknowns, you can't really use the equation. Now, what is this v here? Well, this v is either of these velocities because the velocity is the same. Okay, with no acceleration, there is no change in the initial or final velocity. It's just the same, so it's just 2.4. So I'm going to put in 2.4 times the time, which is 0.35 seconds. Now, if you do the math here, I get a distance in the x direction, or a displacement in the x direction, of positive 0.84 meters. 0.84 meters. Okay, so this marble's going to roll off the edge of the table, and it would go from the edge of the table out to 0.84 meters. That's what that means. That's what you solved. Okay? So that's one type of problem. This problem basically is just something rolls off the edge of something that's elevated and falls to the ground. That's one type of projectile problem. Alright, so this is the same problem from the previous slide. I just transferred it to a slide so I have more space to do some drawing and all that good stuff. So one of the first things to do is, looking at this problem, is to draw the path of the object. And so it says a football is kicked with this initial velocity of 25 meters per second at an angle of 45 degrees with the horizontal. Okay, so basically, if this dotted line is the horizontal, this football is going to be kicked at an angle of 45 degrees with it. Okay, so I'm not certain that that's 45 degrees, but we'll assume that it is. It's kicked at an angle of 45 degrees with a initial velocity of 25 meters per second. Okay. Now the thing is this velocity here has both x and y components making it up. Right? And so until we have this broken into the x and y components, this velocity is actually not that useful to us in terms of using our kinematic equations and that type of thing. Okay, so I'm going to actually start to break this into components, an x component and a y component. And before I do that, though, I'm just going to again confirm with you guys that to the right is positive and up is positive. So anything down or to the left would be considered negative. Okay, because remember, the signs on these numbers is really important. If you get the sign wrong, it's really a shame, but you usually get the answer wrong too. Okay, so I'm going to break this into components, and the way to do that is, remember, I'm going to basically just draw kind of like the x component of this vector, and I'm going to draw the y component of this vector. So I'm going to call this bottom part v initial x, okay, which is something I want to solve for, and I'm going to call this part right here v initial y, which is also something I'd like to solve for. And the angle is 45 degrees right in here. Okay, that's a 45-degree angle. So how do I break that into components? Well, this is just some of the vector stuff that we were doing a few lessons ago. Basically, I'm going to take the trig functions of this, where if I want to get this x component, I'm going to say cosine 45 degrees equals v initial x over the hypotenuse, and the hypotenuse is 25. Okay, and so basically you just do a little bit of cross multiplying here, and you get a v initial x of 17 positive, that is 17.7 meters per second. How do I know it's positive? Because this is pointing to the right. Okay, now what about the y initial velocity? Well, the y is simply sine 45 degrees equals v initial y over 25. And if you do a little bit of cross multiplying here, sine 45 times 25, you get v initial y equals positive 17.7 meters per second. Now this is just kind of a quinky dink. This normally does not happen that your x and y velocities are the same. The reason they're the same is because anytime you take a vector at an angle of 45 degrees, the x and y components are exactly the same. But if that angle had been anything else other than 45 degrees, you wouldn't be seeing this to be the case. So this problem is kind of unique in that regard. Okay, but anywho, now we have components. Okay, I have my initial velocity in the x and the initial velocity in the y. What is the next thing I'd like to do is I'd like to ask myself, is there an acceleration in the x direction, and is there an acceleration in the y direction? Okay, well, in the x direction, is there any acceleration? Is there any force that's causing the football to move horizontally? And the answer is no. No acceleration. Okay, so the acceleration equals 0. Basically, after the ball is kicked, there's nothing that's going to push the ball in the x direction anymore because we neglect air resistance, right? In the y direction, is there an acceleration? There is, and that's negative 9.8 meters per second squared. That's the acceleration due to gravity. That's just going to bring the football eventually down. If there was no gravity, the ball would just keep on going. Okay, that nothing would pull it down. Okay, and that's negative 9.8 meters per second squared. Okay, now what I'm going to do is I'm going to create a chart, and this chart is basically going to compare my x kinematic variables and my y kinematic variables. Maybe I'll make that over here. X, y. Okay, and I'm going to list the 5 variables. All right, and so the 5 variables are v initial. Sorry, I'm not going to even write the x this time. I'm going to show you kind of just a shorter way to do it. V initial, V final, acceleration, displacement, and time. Those are my 5 kinematic variables. And sorry, that says V sub I. I apologize, that looks so crummy. And basically, I'm going to do that for my x component and my y components. Okay, so V initial in the x is, we just figured out, 17.7, positive 17.7. V final in the x, now this is again where you have to use your noodle. Since there is no acceleration in the x direction, the final velocity is actually going to be the same as the initial velocity, so it too will be positive 17.7 meters per second. Okay, you have to be able to realize that because there's no acceleration in the horizontal direction, that velocity will not change. Okay, the acceleration in the x direction is 0. The displacement, I think, is what we're trying to look for, right? We're trying to find the horizontal displacement. So I'm going to put some question marks here because that's something we're trying to figure out. The time of flight is something we're trying to look for too. So I'm going to put some question marks there. What is the time of flight? Now, what is the initial velocity in the y direction? Well, that too is 17.7. We figured that out over here. Okay. The final velocity is going to actually be negative 17.7. How do I know that? Well, this goes back to one of those hints that we talked about in the previous slides, where if I kick a ball, and let's say the ball takes a path like this, when this ball is back to this, or back to its original height, starting height, the velocity is the same, it's just in the opposite direction. So this velocity is going up, this velocity be going down. So it's negative 17.7. It's the same, but it's opposite in terms of direction. And the reason why that is because it's this parabolic nature that projectile motion undergoes. Okay, and so that's something we can take advantage of in terms of knowing the final velocity in the y direction. And so it'll be negative 17.7. Is there an acceleration in the y direction? There is. It's negative 9.8 meters per second squared. The peak height of the football is the d in the y direction, the displacement in the y direction. So like if this is the ground, if you will, we want to know what is the peak height here. Okay, that's y. So we want to know that. So that's something I'm going to put questions for. And then time is just universal. We want to know it because time is the same in the x and y direction. Okay, so the first thing that I recommend doing is trying to figure out the time. Okay, what is the time of flight of this bad boy? So there's a couple equations that we could use, but the one I'm looking at that I think might be interesting, I should say, would be v final in the y direction equals v initial in the y direction plus at. Okay. Now, what is v final in the y direction? Well, we know it's negative 17.7. And this is the beauty of the chart, is now it's just kind of like filling stuff in because you've got all this data right here. What is the initial velocity? Well, it's positive 17.7 plus, what's the acceleration? Negative 9.8 times time, which we're trying to figure out. All right? So if you do a little bit of algebra with that, you get a time of 3.6 seconds. That's how long this ball would be in the air, 3.6 seconds. Okay? So now we know the time. Can I figure out now the horizontal displacement of the ball? And the answer is I can, because if you remember, we talked about an equation where d equals the velocity in the x direction times time. Okay? So this is why we couldn't use this equation first, because we didn't know d and we didn't know time yet. All we knew was v in the x direction. And so now we know time, so I can plug it into this equation. So the v in the x direction is 17.7 times the time, which is 3.6. And if you do that math, I get a distance of about, this means about 64 meters. Okay, I rounded that. Okay, about 64 meters. Okay. Now, what is the peak height of the football? This question is probably the hardest of the three that I ask you. The thing you need to remember is that the parabolic nature of a projectile motion problem, if this thing takes 3.6 seconds, which we just figured out a little while ago, 3.6 seconds to go from here to there, how long would it take to go up to just the peak? Okay, and think about that. If it takes 3.6 seconds to do the whole trip and the peak is only half the trip, how long would that take? Well, I'm going to take this time, I'm going to cut it in half. And if you cut it in half, so I'll call like 1/2 t, that equals 1.8 seconds. Okay, so basically all I did was I divided this by 2. So now that I have that, okay, now that I know that, I can now plug it into one of my kinematic equations. And a kinematic equation I'm kind of liking right now is this one. D equals v initial in the y direction plus v final in the y direction over 2 times time. Okay. Now, here's the tricky part. What is well, we know the initial velocity, right? And I'm actually going to write this up here. I'm sorry, I'm running out of space. This is what happens when you have big handwriting. So what is the initial velocity? And I'll change colors so it's not getting mixed up with this text. So I have d equals, the initial velocity in the y direction is this, right? Plus 17.7. 17.7. And that doesn't look like a plus, so let me fix that. Plus 17.7 plus what is the final velocity? And this is why I'm picking this equation, because it gives me a chance to talk about one other little trick that I didn't mention in the beginning. At this point, at the highest point of a projectile motion problem, at the halfway point, for just an instant, the velocity in the y direction is 0. Okay, it is 0. Think of this problem is hard to visualize because this football is traveling a horizontal distance, but if you throw a baseball up in the air or a tennis ball or whatever you want, throw it up in the air, it goes up, and then for a second it stops and then starts to fall back down. Okay, maybe not even a second, it's probably less than a second, a split second, okay? It stops and then goes back down. That split second is what we're talking about here, and so at that split second, there actually is no velocity, okay? The velocity is 0, and so the v final that we're talking about is actually 0, which makes this easy math in a way, because it's really just 17.7 divided by 2 times the time, which is 1.8, which we figured out right here, okay? So it involves some trickiness because it's real tempting to use this time in the first place because you're thinking, oh, that's how long it took to go that distance. And it's also tempting to use this v final, but that's not the v final we're interested in. That v final happens over here, okay? The v final I'm looking for is the one right here at the halfway point of this motion. So if you do all this math, you should get a vertical displacement, I should really label this d sub y, a vertical displacement of 15.9 meters. And I apologize, I should label this d sub x because who knows what displacement we're talking about. So vertical displacement of 15.9 meters. That takes care of this video. I will see you guys next time.